Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis, and we're in Chapter 12, part of this playlist that I'm calling Tests on Covariance Matrices, and we're going to look at the one sample test for the population covariance matrix sigma. Now the test can be set up like this. The null hypothesis is that the population covariance matrix sigma equals sigma naught, some specified matrix, versus that it's not. Now, sigma naught must be completely specified where the population mean vector does not have to be specified. We collect a random sample of n observation vectors from an assumed multivariate normal population, mean mu, covariance matrix sigma, and we calculate the sample covariance matrix S, and we compare it against the null hypothesized value. If they're close, that's evidence that the null is true. If they're far apart, that's evidence that the alternative is true. Now, a modified likelihood ratio statistic is this. I think this should be an N, but they put an N minus 1 there. And this is it. And then when it can be shown that when H naught is true and the sample size is large, the test statistic follows a chi-square distribution with P times P plus 1 over 2 degrees of freedom. Now, modifications to this exist when n is of moderate size, small to moderate, but we really won't cover that in this video. Now, what's intriguing is this test statistic can be written or expressed in the terms of the eigenvalues of this matrix product, which I find pretty fascinating. We're going to go through that derivation, and then we're going to jump into R and do a test using this approach. So we rewrite the test statistic here, and then this term here, the log of the determinant of sigma naught, if we multiply it by 1, minus 1 times minus 1, we take one of the minus ones up here because it's a log, and then we take it into the determinant, and that's where we get this. The rest of it comes down. We distribute a negative out of that, and I change the order of these terms. The rest of the terms come down. The sum of logs is the log of the product, so that's what we get here. And then the determinant of a matrix is the product of the eigenvalues, and the trace of that matrix is the sum of the eigenvalues. Then the log of a product is the sum of the logs, and then you can distribute that sum, and then I'm skipping a few steps, and then we get this. So the test statistic can be purely expressed in terms of the sample size, the number of variables, and the eigenvalues associated with this matrix product. Now, we're going to do an example in R using Bartlett's test for one sample covariance matrix. Now, there's a FTP site that has quite a bit of data in it, and it's this FTP site here. And we're going to look at T1 or T71 cis-shoot data. Now, they're studying for 30 brands of Japanese wine, however you say that, and they studied the relationship between taste, odor, pH, acidity, sake meter, direct sugars, total sugars, alcohol, formal nitrogen. And we're not going to do a test on all 10 variables. We're going to look at little subsets of it. So I load the data in and read it in, and then I name the variables. And we're going to just look at the first two variables, y1 and y2, and we're going to hypothesize that the covariance matrix is this, 0.2 and 0.1 in the off diagonals. If we look at the sample covariance matrix, then we the covariance of the sample of the first two variables, let's just round it to 3 so it's easier to look at. Now, if we compare these just visually, they're sort of close. Now, to do the Bartlett's test for one sample covariance matrix, well, first of all, we have to use the library MV test, stands for multivariate tests, and this is it. So you put the data in, so the first two columns are hypothesized covariance matrix, and we summarize the results, and the p-value is 0.7, which says there's not enough evidence to reject the null, so we assume that that's the true covariance matrix. Now, just one more quick example, I call it test 2. We're going to look at the first 3 variables of that data set, so it'd be y1, y2, and x1. And I'm going to hypothesize that the covariance matrix is this, and if we look at the sample covariance matrix of the first 3 variables, and I round it to 3 decimals just so it prints a little nicer, yeah, there's some differences, but not too bad. 0.1, this is negative. But if we look at Bartlett's test, we put the data here, so the first 3 columns, the hypothesized covariance matrix, summarize the results, and we get a very small p-value. So that says the evidence that this hypothesized covariance matrix is not the true covariance matrix. Now, if we look at an example from the help menu for this function, they enter a covariance matrix, and let me print it. Now, how they came up with this, I don't know. This is just part of the help menu. And they test to see if the 4 variables in the iris data, which looks at petal length and size, and iris is a built-in data set in R. I don't know if built-in, but it comes with the distribution. So that's the data. We hypothesize that it's this covariance matrix, and we look at the results. The p-value is really small, so there's evidence that this is not the population covariance matrix for the first 4 variables in iris. So, okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.